Welcome to this course, Theory of Yarn Structure. In the last time we started module 5, mass irregularity of yarns. So, in that lecture we talked about Martindale's model. Martindale's model was based on 4 assumptions. So, Martindale considers a sliver which was prepared from many fibers. All fibers were straight parallel to sliver axis, all fibers had same length, the fibers deposited individually and randomly to create the sliver, and the number of fibers present in the cross section of the sliver follows Poisson distribution. Under these 4 assumptions, we derived a relationship of sliver fineness which was equal to mean fiber fineness by mean sliver fineness into square of CV of fiber fineness plus 1. So, this derivation we completed in our last lecture. Also, we established a relation between CV of fiber fineness and CV of fiber diameter, which is often valid in case of wool fiber. So, in that case the relation was CV of fiber fineness was equal to 2 times CV of fiber diameter. Then if we substitute, then we obtained plus 1. So, often you will see in many articles and also books this expression used for to find out the CV of sliver prepared from wool fibers. So, in this lecture we will first discuss about the effect of doubling on mass irregularity. So, what is the effect of doubling on mass irregularity of sliver? Almost all of us knows about doubling. Doubling is basically combination of slivers. So, when we combine or when we put one sliver beside another sliver, we call doubling is equal to 2. When we place 3 slivers side by side, we say doubling is equal to 3. So, doubling basically refers to combination of slivers. Now, often we see in draw frame, in a roller drawing machine, we feed 6 to 8 slivers, that is doubling is equal to 6 to 8, and we obtain a drawn sliver. Why do we do that? In a simpler form, to say doubling reduces mass irregularity of sliver. How it is done? So, in this lecture we are going to learn about that. So, what is the theoretical basis that doubling reduces mass irregularity of sliver? That is what we would like to learn today. what we see here is m number of slivers. This is sliver number 1, sliver number 2 and likewise till mth sliver. This sliver fineness is denoted by T subscript 1. Of course, T 1 is a random variable. Second sliver, the sliver fineness T subscript 2 is also another random variable. Mth sliver fineness T subscript m, which is another random variable. Now, each sliver is different. They are different in terms of fibers, fiber parameters, they are different in terms of fineness, they are different in terms of their irregularity. Sliver 1 has a mean fiber fineness T 1 bar, coefficient of variation of fiber fineness V T 1, mean sliver fineness capital T 1 bar and coefficient of variation of sliver fineness V T 1. V T 1 can be obtained by using Martindale's model. V T 1 is equal to T 1 bar by this V square T 1 plus 1, right. Now, we come to second sliver. The mean fiber fineness T 2 bar, CV of fiber fineness V T 2, mean sliver fineness capital T 2 bar and CV of sliver fineness V T 2. This expression also can be obtained similarly by using Martindale's model. Now, we come to mth sliver, mean fiber fineness small t subscript m bar, CV of fiber fineness V T subscript m, mean sliver fineness capital T subscript m bar and CV of sliver fineness V capital T subscript m. This can also be found out by using Martindale's model in a similar manner. Right. Now, so if we double, then we will obtain one sliver, that is called double sliver. Okay. So, let us first characterize these individual slivers. So, we can now consider one particular sliver, say jth sliver. So, what will be the mean value? Mean sliver fineness is this, and the CV will be this. So, these are the, and also the variance will be is equal to this, right, because C v square is equal to variance by mean square. So, variance is equal to C v square into mean square. Okay. Now, what about the doubled sliver? For the doubled sliver, so if we combine all these individual slivers, we will form a double sliver. That double sliver will also have a mean of sliver fineness. That mean T bar will be equal to summation of all means right, and it will also have a variance dt. These variances will be all additive. Also, it will have a coefficient of variation. This. So, left hand side are the characteristics of individual slivers, right hand side are the characteristics of double sliver. We need to find out the expression for C v of fineness of double sliver. So, T bar is equal to this, j is equal to 1 to m, okay, and dt is equal to summation dtj. All variances are additive in nature. Now, v square T j into T j bar square. We will substitute this from Martindale's model. Right, sorry, this one will cancel. So, the final expression for variance is this into this. Okay. So, if this is the expression for variance of the double sliver, then the C v of fineness of double sliver will be V t is equal to d t by t bar, or we can square it dt by t bar square, right. So, we can write summation j is equal to 1, j is equal to m t j this v square t j plus 1 divided by t bar square, and if we take the root, then square. Also, we can write this expression in this manner. And j is equal to 1 to m, right. So, this is the most general expression for the CV of fineness of doubled sliver. Summation, this is the fineness of individual fineness of jth sliver, fiber fineness of jth sliver. This is the mean fineness of the double sliver. This is the fineness of jth sliver. This is the mean fineness of double sliver. This is the square of CV of fiber fineness of jth sliver plus 1. Now, look at this fraction, mean fineness of jth sliver divided by mean fineness of double sliver. So, this is the mass fraction of jth sliver. So, this is the mass fraction of jth sliver, right. So, this is the most general expression. Now, we will consider a very special case. Let us assume that all fibers are same, that means T 1 bar is equal to T 2 bar is equal to T bar. Then their CV will also be same. So, they become constant, right. Also we consider that the fineness of all slivers are same. That means, T 1 bar, T 2 bar, T m bar, which is equal to capital T bar by m, right. Why? Because capital T bar was this. Okay. Then what we obtain is, let us rewrite here we will write T bar by m. So, this is your T bar, this is your this is T bar by m and T bar is there already. Okay. We can write this as so 1 by m T bar by this v square T plus 1. Okay. So, further we can write it as V T is equal to one by m T bar by this into v square T plus 1. So, this becomes a constant. So, we can write V T double sliver is the C V of individual sliver by root over m, right. So, you have often seen this expression C V of doubled sliver is equal to C V of individual sliver divided by number of doubling. So, this expression is a very special case, not true always. It holds true only in one case, when all fibers are same, their mean fineness same, CV coefficient of variation of fiber fineness same, and also all individual slivers have same mean fineness, then only this expression is true. Otherwise, if all individual slivers are very different, then you will find out the CV of double sliver by using the most general form that we derived few minutes before, right. So, this was about effect of doubling on mass irregularity. Now, we will consider a very interesting situation. Suppose fibers are not parallel to the axis of the sliver. Suppose the fibers are inclined at an angle from the axis of the sliver. What will be about the irregularity of that sliver? Why we think about this? It is a very special abstract case. We would like to learn the effect of fiber inclination on mass irregularity of sliver. So, what is the effect of fiber inclination on the mass irregularity of sliver? This we would like to learn now. Effect of fiber inclination on the mass irregularity of sliver. Suppose let me draw two slivers. This is one, second is this is the axis, and here also this is the axis. This is suppose sliver A, this is suppose sliver B. Which of these two slivers will have higher mass irregularity? And why? So, this is our basic question. What do you think so? Sliver A will have higher mass irregularity than sliver B, or the mass irregularity of sliver B is higher than that of sliver A? So, let us solve this abstract case now. So, what you see is that this is a diagram of a sliver with oblique fibers. So, all fibers are inclined at an angle theta from the axis of sliver. In that case, what will be the CV of fineness of this sliver? Now, in order to solve this problem, let us imagine a simple situation. What you see here, a fiber of length L, which is also inclined at an angle theta from the axis. What do we do? The cross sectional area of this fiber is S, but the sectional area perpendicular to the axis of this fiber is S star. Obviously, S star is greater than S. Now, what do we do? Imaginatively, we divide this L into many segments, many infinitesimally small segments. Then we drop each segment along the axis of the sliver. So, we obtain a fiber what we call as obviously an imaginary fiber. So, this is called as effective fiber. As a result, we obtain an effective fiber. Of course, this is imaginative. This fiber will have a length L star. So, the inclined fiber has a length L and this effective fiber has a length L star. What is the relation between L star and L? Into cos theta, right. This oblique fiber has a cross sectional area S, this effective fiber has a sectional area S star. We refer to our module 1 where we defined and derived this relation. What is the relation between cross sectional area of a fiber and sectional area of a fiber which is inclined at an angle theta? So, this relationship we derived in module 1. Then what is the fineness of this effective fiber? T star we know from again module 1. This is the expression for fineness. S by cos theta into rho. So, S into rho by cos theta. What is S into rho? S into rho is T. T is the fineness of oblique fiber into cos theta, right. So, fineness of the effective fiber or imaginative fiber is equal to the fineness of oblique fiber divided by cos of the angle of inclination. When theta is equal to 0, cos theta is equal to 1, T star is equal to T. When theta is greater than 0, then cos theta is less than 1. So, T star is greater than T. So, the effective fiber will be coarser than the oblique fiber. when they are inclined at an angle theta. What will be the mean? This mean will be cos theta is a constant and expectation of t will be t bar, right. So, t bar by cos theta, this is the mean. What will be the variance? Variance. Variance of this is this is the definition of variance. T star is t by cos theta. Expectation of t star, that is t star bar is by cos theta square. Now, cos theta is a constant. So, the constant will come this. So, what is this? This is the variance of t. Right. Then what will be the CV of t star? So, coefficient of variation. That is equal to this. What is this? This is variance of this divided by mean of this. Variance we have just now derived, one by cos square theta into variance of t, mean of t star, mean of t by cos theta. So, this cos theta will cancel out. As a result, what is left is variance of t by mean of t, that is equal to coefficient of variation of t. So, this is a very interesting result. What we see is that whether a fiber is inclined, it does not matter so far CV of fiber fineness is concerned. So, CV of an inclined fiber and CV of fineness of an inclined fiber and CV of fineness of a straight fiber is same. That is what we obtain from here, right. This we substitute in original Martindale's equation. So, V t is equal to T star this into V square T star plus 1. This will be the CV of fineness of sliver with inclined fibers. Now, we substitute cos theta T bar, this does not change this. So, what we see is that one, right. So, what we see is that because of the inclination, the sliver, the CV of sliver fineness is higher. So, if theta increases, V t increases. Higher is the inclination of fibers, higher is the mass irregularity of the sliver. So, if we come back to our starting question, which of these slivers will have higher mass irregularity? Of course, sliver B is the answer. And why? This complete derivation answers this question why. Right? Further, what we see is that when theta tends to pi by 2, that means fibers are perpendicular to the axis of the sliver. Right. In that case, cos theta, theta tends to pi by 2, this tends to 0, this is very small. When this is very small, this fraction is very high. So, V t tends to infinity. So, the mass irregularity of the sliver theoretically tends to infinity when the angle of inclination tends to pi by 2. So, when all the fibers are parallel to the axis of the sliver will exhibit enormously high mass CV. So, this very interesting, however abstract situation gives us some interesting information. Now, we will discuss a few important attributes of mass irregularity of sliver. The first of it is limit irregularity. There exists a concept of limit irregularity. This limit irregularity is often expressed by I is defined by actual experimental mass CV divided by limit CV. That means, CV actual by CV limit. Now, there is a testing instrument so called Uster tester, Uster evenness tester, which measures the mass irregularity of sliver, roving, yarn, and it actually measures. So, we obtain actual CV from experiments. CV limit we can calculate using Martindale's model, this CV limit, and if we divide CV actual by CV limit, we obtain limit irregularity. So, it is not limit irregularity, it is index of irregularity. I am sorry. This is index of irregularity. So, index of irregularity I is defined by actual CV by limit CV. Uster tester measures actual CV, limit CV can be obtained from Martindale's equation. If we divide, then we obtain index of irregularity. What we observed is that index of irregularity I is too high sometimes. For yarn, this index of irregularity found to be this range. What infers is, if we consider index of irregularity is say 2.58, which is often found, then actual CV is 2.5 times higher than limit CV. This clearly indicates that Martindale's model is not too precise. Had it been precise, the index of irregularity would have come close to 1, but it is 2.58 times higher. Actual CV is 2.58 times higher than limit CV. That means, there is something imprecise in Martindale's model. There exist a few corrections in literature. One of the corrections, empirical, has been given by the company Uster. Uster. They have given this correction as CV limit is equal to this A and B are parameters. So, this empirical correction was suggested by the company Uster. If we write this, so V t is equal to A by B. Okay. Then what happens is that if we take logarithm both side, right. So, if we plot this along y axis, this along x axis, we obtained a linear curve. This so called Uster statistics. How does this curve looks like? This curve looks like this Uster statistics. So, V t is equal to A minus B ln t bar. This is y, this is x, we obtain a linear curve. So, if t bar is text, so starts from here to here, so from here to here, and if we look from this side to this side, it is basically any, and 5% of the textile companies considered by Uster shows this trend. 25% of the companies in the world surveyed by Uster shows this trend. 50% of the companies worldwide surveyed by Uster shows this trend. 75% of the companies surveyed by Uster shows this trend, and 95% of the companies worldwide surveyed by Uster shows this trend. So, this is how you should read Uster statistics curves. So, this is linear because of this function. So, this is one of the empirical corrections of Martindale's model. However, this is completely empirical, it does not give any insight of what is not too correct in Martindale's model. Probably a better formulation was given by Burnett. Burnett's idea was also empirical, however, he tried to analyze Martindale's assumptions little deeply. What he thought is that Martindale's model had 4 assumptions. Fibers have same length, it is acceptable. All fibers are parallel and incline and parallel and to sliver axis and they are straight, also to some extent acceptable. Fiber numbers in the cross section follows Poissonian distribution is okay. Fibers deposit individually to form a sliver. This assumption was questioned by Burnett. What Burnett thought that when fibers in a drafting system, when fibers move, they move together in clusters. So, some fibers agglomerate, they form a cluster, that cluster moves to form a sliver. So, that was Burnett's idea. So, what you see in this image is it is a Martindale's model, one fiber and then sliver. Here it is cluster and then sliver. So, Burnett probably thought this is not correct. However, this is correct, that is what Burnett thought. Then he empirically suggested one relation. This is the mean fineness of cluster by mean fineness of fiber 1/4, mean fineness of sliver, fineness of fiber to the power 1/3. This relation was empirical. So, he proposed this relation. This is the mean fineness of cluster, mean fineness of fiber, mean fineness of sliver, mean fineness of fiber. Then we can write by bar is equal to T c by T bar into T bar by this. This is equal to 1/4 T bar by this to the power 1/3 T bar by this. So, 1/4 2/3. Then we can write irregularity of this sliver will be this divided by 2. What will in Martindale's expression, if you substitute this, if you substitute small t bar by capital T bar by this, then you will get this form. So, in Martindale's model, small t bar by capital T bar, this expression you substitute by this form, then you will obtain this expression. And this value is numerically higher than that obtained from Martindale. So, this empirical correction he suggested. So, these two empirical corrections are existing in textile literature. However, Burnett's idea or this expression has a serious problem. If I try to obtain this graph, say this value is 64, then what will obtain, this value will be equal to 1. If this is less than 64, then this is not possible, because this will be imaginary part. The fineness of cluster cannot be less than the fineness of fiber. However, this is the real part. So, if one has to use this expression, you need to be sure that the cross section of the fiber, the cross section of in the cross section of sliver or yarn, number of fiber must be greater than 64, then only you should be able to use this expression. If a yarn is having less than 64 numbers in the cross section, then this expression cannot be used, because this expression has a serious problem. It does not define when number of fibers is less than 64. If it is more than 64, you can use this expression. So, we stop here. In the next class, we will further discuss about mass irregularity of sliver. Thank you very much for your attention.